In our last lecture, near the end, we were concentrated on probabilities. The quantum world is ruled by probabilities. It's not a world in which definite outcomes can be made for a prediction of an experiment. When we consider the first generation of string theories, these are quantum theories, so the rules of probability must apply there. But the string is more than a particle. The string has lots and lots of what we can think of as notes. And from our perspective, those notes look like particles. So in order to get the probabilities to work out for most of the notes of the strings, it turns out that it's sufficient to add in 22 extra directions. And so the Einstein hypotenuse becomes this horrible thing that we see on this transparency, where we get links not just associated with our three spatial directions and time, but we also have links associated with all of these extra directions. And this works for most of the vibrations of the string. However, that's not the end of the story of probabilities for this first generation of string, also called the bosonic string. Because in our world, if you look at the Einstein hypotenuse, it has the form that I've written here, where the mass square term on the right side of this equation has a plus sign in front of it. For most of the vibrations of the strings, as long as you add in the extra 22 dimensions, this plus sign also applies to those vibrations. However, their probabilities for one object of the bosonic string has a minus sign there. And that's the tachyon that we met at the end of last lecture, the monster that threatened to destroy the mathematical description that is coming from string theory. This lecture, we are going to find out how to tie this monster up. Remember, I talked about Pandora's box. If we had Pandora's box, we could perhaps put the tachyon inside and then seal the box shut and mathematically have a safe universe that looks like ours. There's a way, it turns out, to do this. Now, getting there is going to be a little bit strange, and I'm going to have to tell some stories, and I'm going to need your imagination for this purpose. So let me first remind you of an aspect of our world that we've talked about on several occasions, namely that the quantum denizens almost all spin at a fixed rate. The electron spins at a rate 1/2 h-bar. All of the quarks spin at a rate of a 1/2 h-bar. So if we start our movie going here, what we'll see is this little ball up in the upper left-hand corner can be set spinning, and there it goes. We call it a quark in this picture. In the string theory that we have talked about so far, there's something quite remarkable about the notes, its vibrations. Every single vibration of the first generation of string that we have talked about spins at a rate that is either 2, 4, 6, 8, or any even integer times the rate of spin of the electron or the quark. Now, back when we visited the world of the quantum, remember, spin was a very important quantity because things that spin at the rate of the electron, for example, if you tried to put two of them in the same place, they would repel each other. But things that spin at twice the rate of the electron or 4 times the rate of the electron could be put at the same place at the same time with no difficulty at all. That's the difference between fermions in the former case and bosons in the latter case. And we can see from this first generation of string that every kind of note, every kind of oscillation associated with the string was a boson. But wait a minute. The mathematics is all bosons? That can't be our world. The electron is not a boson. The electron's a fermion. And so the first generation, even after we have fixed these problems, cannot possibly describe our world because it has nothing in the mathematics that looks like an electron. So this old first generation of string, in addition to having the tachyon monster, doesn't have electrons, doesn't have us. So that's a problem we're going to have to try to fix. We're going to fix this problem by first starting with a little game. Let's imagine that I had a bicycle wheel that was spinning here, spinning, say, like this, and I put my hands around the bicycle wheel, and then depending on which way it's spinning, I'll close either my right or left hand. If it's spinning this sense, I'll close my right hand. If it's spinning in the opposite sense, I'll close my left hand. That's what we physicists mean by spin, basically, that particles have a property that we can either associate it with closing your right hand or closing your left hand. And those two things are different. You might not think so, but let me show you why they're different. I can hold my hand like this and close it. Notice the sense in which the motion is occurring from this side over to this side. In order to get that to happen with the other hand, I have to hold it upside down. So spin up, spin down, right hand, left hand. So let's imagine that we have our bicycle wheel and we figured out that it's spinning in a right-handed sense. So it's spinning with the wheel coming towards me in this sense. Well, I can imagine painting a little arrow there and walking around the arrow once. So let me place myself here and have my imaginary wheel here spinning with its arrow pointed towards me. I look at it. And then I look away and walk all the way around and come back. And then turn and look at the wheel again with its arrow. What do I expect to find? Well, unless some one of you have come and somehow disturbed my experiment, I expect to find the arrow pointed at me again, right? And that's a natural expectation. In fact, you can do this with real spinning wheels with putting arrows and you can see that it works. However, let's imagine something a little bit different. Let's imagine that we have not me, but an observer some distance away, and I blindfold the observer. I say, look at the wheel, and I blindfold the observer, and then guide them around the wheel one more time, bringing them back to the same spot and take the blindfold off, and then ask them, did anything change? They would probably say no, unless the wheel, let's say we're spinning really fast, so it, doesn't slow down. They'll say, no, arrow's still pointing at me, wheel's still spinning at the same rate. And again, you'll say there's nothing science fiction about that. It sounds like the way our world works. Well, let me tell you about something that is not like this world. The behavior that we just described, where you walk around an arrow once and you look at it at the beginning of the walk and at the end and you find the arrows pointed in the same direction, mathematicians have a name for that kind of a quantity. They call it a vector. So a vector is like an arrow. You walk around it, it points in the same direction. There are things that don't have that behavior. The simplest example I can give you is a little ball. If I put a ball on the ground and look at it, a ball that's perfectly featureless so that you can't distinguish one side or another. So I put it on the ground, I look at it, and then let's say I walk not all the way around, but halfway around the ball. And I look at the ball, it looks pretty much the same. Or I walk 3/4 of the way around and look at it. It still looks the same. So there are things in nature that don't depend on the orientation, how far around you go before you've seen the same shape. Mathematicians have a word for those kinds of objects also. They're called scalars. And it turns out that in the quantum world, the things that a lot of the objects that we have met have that kind of property. For example, the photon, which is the carrier of the electromagnetic force, behaves like a vector. On the other hand, the mysterious Higgs particle, which we're going to come to and talk about in later lectures, behaves like a scalar. But you'll notice in our visit to the quantum world, there were lots of other objects, and I haven't talked about their behavior at all. For example, the electrons and the quarks. So how do they behave? So now let me give you something that sounds like science fiction. Let's imagine, once again, we had our spinning wheel with its arrow pointed out to one side, and we stand and we look at it, then we blindfold ourselves or have someone blindfold us, and we walk around it exactly once, the blindfold is removed, and we turn and look at the wheel, and we find the arrows pointed in the opposite direction. Now, in the real world, if you saw this, you would say, someone's playing a trick on me, because clearly when I was blindfolded, someone took the bicycle wheel and turned it in the other direction. That would be a very natural conclusion to reach. Well, let's continue our thought experiment. Instead of walking around once, let's say you walked around twice. So you were blindfolded. First you looked, blindfold, once around, twice around, blindfold removed. You look at the object and it's pointed directly at you. Again, not such a surprise. You would say, well, whoever is playing a trick, they didn't do it this time. Suppose I told you that there are objects in our universe that if you conduct this experiment upon them, you find out that you walk around once and they're pointed in the opposite direction. You walk around twice and unblindfold, you find they're pointed towards you. You walk around 3 times, they're pointed in the opposite direction. You walk around 4 times again and look, they're pointed at you. And any odd number of times around, you find them pointed away. And any even number of times you walk around them, you find that they're pointed towards you. Now, in our everyday experience, if you actually did this with, say, a bunch of children, they would conclude that some funny game is being played. But in the quantum world, it turns out, there are things that have that behavior without any funny games being played. These things are called spinners. So a spinner is like an arrow that when you walk around it once and look at it, it's pointed in the opposite direction, but you'll walk around it twice and it's pointed towards you. A very strange thing. Well, spinners were actually first seen in mathematics. Like much of what goes on in string theory, it's a story which interweaves mathematics with our world. And in 1913, a mathematician named Élie Cartan was the first person to write a mathematical description which described this strange behavior where even numbers of times it points at you, odd number of times around it points away from you. These were discovered in a mathematical construct known as Clifford algebras. And Clifford algebras, it turns out, was even older. It's a piece of mathematics that was due to an English mathematician, Clifford, who lived between 1845 and 1879. So these things have been known in the mathematical literature since the mid-1850s, that you could write mathematical things that had this weird behavior. But of course, who pays attention to mathematicians except other mathematicians? So nobody cared. In the 1930s, however, a physicist by the name of Wolfgang Pauli, and then later joined by Dirac, showed that this strange behavior can be used to describe things in nature. And in fact, they wrote down equations. Remember, we've talked about Dirac before. He's the guy who wanted to write the equation that describes the electron consistent with the laws of special relativity and consistent with the probabilities of the quantum universe. That's Dirac. They found out that the mathematics requires this funny flipping back and forth depending on the number of times you walk around it. Now, again, you might say, gee, Professor Gates, that can't be our world. The only problem with that statement is it is our world. And we know this from a very famous experiment conducted in 1921. It's called the Stern-Gerlach experiment. And what you do in this experiment is very simple. You take an electron beam and you shoot it through an area where there are magnets on the outside. Now, from the time of Maxwell, we have known that when an object spins and has charge, it acts just like a bar magnet. And so if you have 2 bar magnets, you're used to the idea that if you take 2 bar magnets and let's say this is the north pole of one and this is the north pole of the other, if I put them north pole to north pole, they push themselves apart. Or if I put it south pole to north pole, the 2 magnets attract each other. So now let's try to put this all together. Spinning objects behave like magnets. So if we shoot a beam of electrons down a path, it's like shooting a bunch of little bar magnets. But then we can take real magnets and put them around the path, and therefore, just like the bar magnets we talked about, they'll be pushed around by the external field. Now, the thing that's interesting about how strong the magnet is, it depends on the rate of spin. If it spins very fast, it's like having a big bar magnet. If it spins very slow, it's like having a small bar magnet. And so therefore, by measuring the push, you can measure the rate of spin of the electron. It's a very simple idea, I hope. So this experiment was done by Stern and Gerlach. And they used it, in fact, to measure the spin on the electron. And what they found, most remarkably, is that the spin of the electron only came in 2 numbers. It's what we've been saying before. It spins at a rate of h bar in a positive sense, or it spins at h bar in a negative sense, but it never spins at any other rate. So here in the laboratory, we had found the rates of spins are quantized. This is what we mean by the quantization of spin, that either can be what we call spin up or spin down, but that's it. Now, once you know that you have found an object in the laboratory that has this behavior, you can then do the experiments of walking around and doing the measurements. And when you do these experiments, what you find is exactly the flipping behavior that I talked about before, where you walk around twice, it looks like it's pointed at you, but you walk around, say, 3 times, and it's pointed away. All electrons exhibit this behavior. All quarks exhibit this behavior. And in fact, this behavior is the secret of chemistry. That's why we can put 2 electrons in the lowest energy shell of an atom, because one of the electrons has its spin up, but the other one has its spin down. At the next level of the energy of an atom, we can put 8 electrons. 4 of them have their spins up, 4 of them have their spins down. And so this notion of spin is intimately connected with chemistry. So it's a very bizarre kind of world, this thing about spin, because you see, spin also means that we're talking about objects that behave like little spinning objects, but they have no size at all. How can that be? You know, with a real object, if we had a ball that sits here, we sort of look at it and we watch it rotate. Or in my animation for the quark, we saw the letters quark going round and round. So we know it's spinning. But let's imagine that we take that little ball and shrink it to nothing. Then how do you know it's spinning? Because you can't see any markings on it. Well, due to the Stern-Gerlach experiment, we can measure to see if it acts like a bar magnet. And that's what happened in 1921. And we found this remarkable result, that spin is quantized. Now, as I said, spin is ubiquitous in the quantum world. All of our denizens have spin. To recapitulate, all electrons and all quarks spin at the same rate, this number 1/2 h bar. But the photon, that's the force carrier for the electromagnetic force. The intermediate vector bosons, those are the force carriers for the weak nuclear force. The gluons, which are the force carriers for the strong nuclear force, every one of those objects spins at twice the rate of the electron, not the electron rate. They're all bosons. You can put as many of them in the same place as you want at the same time. So, this notion of spin distinguishes the world, and it turns out that because of its discovery in the 1920s and then in the 30s with the work of the physicist Pauli and Dirac, who put the mathematics consistently to describe the experiments, we got quite comfortable with the notion of spin. So in the 1970s, when string theory was being discussed, the notion of spin was, for theoretical physicists who were looking at particle physics, there was nothing odd about this notion. It had been around for about 40 years. Lots and lots of people knew how to manipulate the notion of spin. But in this first generation of strings that we talked about, where the vibrations are either twice the rate of the electron, or 4 times the rate of the electron, or 6, or any even integer, or possibly 0, because the tachyon turns out to be a spin 0 object, there string theory was in trouble. So, what to do to fix it? Well, some clever young physicists were around then, and 3 of them were André Neuville, Pierre Ramon, and John Schwartz. And in fact, Schwartz had been one of the people involved in discovering the tachyon monster. So he was very intimately aware that this thing was there, and if there was no way to put it in the Pandora's box and keep it locked there, it would destroy this idea of string theory. Now, these 3 young physicists did something that is often the case in physics, that innovation often comes from young people. In physics, when you look at the kind of fundamental physics that is associated with string theory, advances come from fresh minds who bring a new perspective to the problem. These young people did precisely that around 1971. What they did was to include the missing notes. What do we mean by missing notes? Well, instead of things that spin at even integers, times the rate of the electron? How about including objects that spin at odd integers times the rate of the electron? An odd integer includes the integer 1. If you do that, you then get some mathematics that includes the electron, because 1 times 1/2 is 1/2, and that's what we need for an electron. But you also can get any other odd integer, so you can get 3/2 or 3 times the rate of the electron. That's an object we've never seen in the laboratory, and in a future discussion, that object called a gravitino is going to play a very important role, so we'll come back and look at that. Or there are higher spin objects. So, using slightly different mathematics, Neveu and Schwartz on one hand and Ramond on the other found out how to put spin into string theory. It is as if you think of the string as a piece of spaghetti, what these guys did is wrote the equations that allow it to spin on its axis. We can say that in a prosaic sort of way about what was going on. Now, once you put spin into the game, you pass into the second generation of string theory. It is not the generation that we talked about before, which is a bosonic string. We're now at the level of the spinning string. So the spinning string has electron-like objects. That means some of its notes obey the Pauli exclusion principle. Others of its notes do not obey the Pauli exclusion principle. Again, in our visit to the world of the quantum, that's how our world looks. The force carriers do not obey the Pauli exclusion principle. The objects the forces act upon do obey the Pauli exclusion principle. So at a very minimum, you can conclude that the second generation of string theory, things that we call the spinning string, look more like our world. They have this same kind of dichotomy. Now, we still got the tachyon out there, and it's still destroying all of the physics that we know. Let me say something more about how it's only the tachyon that makes this destruction. Because after all, the string has an infinite number of modes, and I argued earlier that it is a calculation. Let me emphasize this. It's a calculation that one has to perform to find out that in order to get the probabilities to work, you need these extra dimensions. The mathematics which proves that is actually quite old. In fact, it goes back to an Indian mathematician by the name of Ramanujan. Ramanujan was a remarkable character. In fact, Ramanujan started doing important and deep investigations in an area of mathematics called number theory. And the way that he was discovered, which is itself an interesting story, was he essentially sent a message to an English mathematician by the name of Hardy. And in this message to Hardy, he wrote some equations. Hardy, looking at the equations, realized that they were of a character that had never been seen anywhere before. And not only were they of a character that they had never been seen anywhere before, but in fact, they expressed the absence of something. Now, from our point of view, our modern point of view, what this absence of is it's the absence of probabilities outside of 0 and 1 that these equations describe. Now think of this. 70 years before string theory was invented, there was a mathematician who showed that by adding up certain balanced sets of objects, you could get probabilities to work. And he never even heard of string theory. This is another example of what we mean by unreasonable effectiveness, where a piece of mathematics that you might think has no connection whatsoever to physics, often in history, later shows up and then cures a problem that physicists are concerned with at this later stage. Ramanujan's work is quite remarkable in many, many ways, including his habits. Hardy once made a statement, which I'll paraphrase, which was, some of the things that Ramanujan wrote had to be correct because nobody could imagine things that would come close. Ramanujan himself said, an equation is uninteresting to me unless it expresses a thought of God. So these are people clearly with a sense that they're on to a deep truth about our universe, but it's something that should be of overwhelming importance. Unfortunately, Ramanujan died at a relatively young age, having made a number of conjectures, which even to this day in mathematics are the source of some controversy and research. That shows you the depth and power of his thought. But some of his identities are exactly the ones we need in order to show that the probabilities work for most of the oscillators or most of the notes of the string. So we have, with spinners, more notes. And remember the tachyons lurking out there. So you can sort of see where the story is going to go next. Since the notes associated with the even spin rate objects were not sufficient to put the tachyon in a box, then maybe, just maybe, with the notes that come from the odd spinning rate notes, we will be able to tie the tachyon into a box. And in fact, that's exactly what's going to happen. We're going to talk about this in more detail later, but I just want to give you a sense of it. The extra spinning notes have a property associated with them that binds the tachyon in a box. In fact, it actually gets rid of the tachyon entirely. We physicists say it removes the tachyon from the spectrum. So, string theory in the second generation is almost safe. There's one more important step that we need to take, but we're now starting to learn how to tie the tachyon into a box. All of the formulae for area that we've talked about, those work just fine for all of the remaining notes of the string. And now, how do we get rid of the tachyon? That's the goal. The process turns out to lead back to symmetry. So we're going to have to learn one more symmetry. Remember tilting the ladder and how the area of the square on top and the square on the bottom were always the same. Even if we tilt the box upward, then the areas on the side equal to the area of the ladder. That's symmetry. So now let me tell you one more symmetry, a very strange symmetry. Among the notes of the string, we have the bosons and we have the fermions. The bosons are like the force carriers in our world, and in fact include objects that are the force carriers. The fermions are like the quarks and the leptons. One obeys the Pauli exclusion principle if we're talking about fermions. The other does not obey the Pauli exclusion principle. So you would start off by saying these are very different things. However, when I talked about our ladder, remember our ladder could lay flat on the ground, so you might say this direction flat is very different from going up and down. And in fact, if you fall out of the house, you know that they are different. But nonetheless, when we tilt the ladder on the side of the house, in some sense, these two directions are kind of the same because they contribute the same to our Pythagorean theorem. So, that's the notion of symmetry. And here we see it illustrated in this diagram. Let me run this backwards so we can once again remind ourselves how this works. If our ladder is laying flat, the area of the green and blue are the same. If we begin to lift the ladder along the wall of the house, then we say that the area of the green is equal to the area of the brown plus the area of the blue. That's symmetry, that something is equal to something else. And then finally, as we pull the ladder away from the wall, a new area appears, that's pushing the bottom of the ladder to the side, and then it's the sum of the blue, the brown, and the purple that equals to the green area. So now, let's go back and sort of in our mind's eye, imagine that the blue box represents the bosons of the string, and the brown box represents the fermions. So let's just say that roughly speaking, this is how these objects behave. Then you would say that it should be possible to trade, and that's like lifting and lowering our ladder, to trade the size of the blue box for the size of the brown box. And yet, they would always have to be equal to the area of the green box. That's what we mean by symmetry. We call it supersymmetry because things like the electron are being traded for things like the photon. This idea is so radical that it's only 30 years old. Up until the 1970s, no one had ever thought that you could trade electrons for photons. It just seemed just totally outrageous. The mathematics for photons comes to us from Maxwell. The mathematics for electrons come to us from Dirac. They're very different mathematics. So how can you trade these things? In the next lecture and some subsequent lectures, we're going to explore this idea of how you trade, but it turns out that the brown box has associated with it a minus sign. Very similar, in fact, to Einstein's hypotenuse. This minus sign, when appropriately used, is going to bind the tachyon. And when we do that, we will travel beyond the world of spinning strings to a new level. We get to what are called superstrings at that level, the ones where the tachyon is permanently removed from the physics, or rather the mathematics of these models, and therefore the physics of these models is safe and looks like ours. Has probabilities between 1 and 0, and has no tachyon